Hello everyone. This doesn't work, but it's okay. Welcome to today's Séminaire Général de l'IPHT. It's a very great pleasure to have here Julio Parra-Martinez, who braved and crossed the vet to come to us today. And so he's going to tell us about black hole collider physics.
Thanks a lot, Carlo, and thanks for the invitation. It's very nice to come here. I've been here a few times, but particularly excited to meet the people that I don't know already. So I'm going to give this talk, which is not for the experts. So I'm going to apologize, first of all, to the experts, because I'm not going to say anything very new. In fact, as you can see, I have a typo even on the cover that the last time I gave this talk was a bit over a year ago, or a version of this talk. And I'm going to kind of leave out many developments that have happened since. But at least I'll try to give a flavor of what this research program is about. Okay, so what do I mean by black hole collider physics? Let's go to the beginning. And I think we are in a very exciting new era of gravitational physics. We have many new experiments probing different aspects of general relativity, have gravitational wave detectors already on the ground, like LIGO that have detect gravitational waves, also upcoming detectors that will be in space. There's pulsar timing arrays that have measured very long wavelength gravitational waves. We've have the first images of black holes directly with radio waves. So we are probing gravity in new regimes that we didn't probe it before. And I think there's many lessons ahead. Hopefully we'll learn about things like strong field gravity, maybe primordial gravitational waves. We are learning already many things about the population of black holes and other compact objects in the universe, like neutron stars. We hope to probe the equation of state of neutron stars and learn some nuclear physics from that to test general relativity, especially in this strong gravity regime, and much more. Okay, so these are experiments. We don't know what we will find out there. So I think it's very exciting. And the question that I asked myself a few years ago when I saw all of these new things coming up was, can we as theoretical physicists and particular particle physicists contribute to this amazing effort? And okay, here I have some pictures of some places where, okay, maybe perhaps expectedly we can use tools from particle physics to study colliders. But perhaps less expected is that the same language is used to study many-body physics, the physics of phase transitions and certain materials, or even the physics of the early universe. Okay, so the goal of the talk today is to explain that we can use the same toolset, ideas from quantum field theory, scattering amplitudes, other ideas from particle physics to shed new lights on the physics of gravitational waves and these kind of new experiments. Okay, so what are scattering amplitudes? There's a Feynman diagram missing here, but just ignore the blank. Okay, scattering amplitudes are the quantum mechanical probabilities of scattering events with some particular energies and polarizations and angles, right? We are all familiar from this. Okay, so we can have, okay, so this is how I will be depicting amplitudes from now on by some little blob with some legs coming in and some legs coming out. Okay, and okay, you should think of these as particles that come in, maybe interact. So these are particles deflecting gravitationally. Maybe there's some scattering angle. But in the quantum theory, many other things can happen. And then from these, usually we just compute cross sections. We take the absolute value squared to get a probability. And this is what we compare with the experiments where we look for, say, some peak for certain energies to detect new particles in colliders. Okay, so this is all data from LEP. Okay, but what we measure in gravitational wave detectors are these in-spiral processes. They're kind of a pair of black holes or compact objects kind of moving around each other in orbit, losing energy in the form of gravitational waves, and eventually merging, right? And also these are black holes and neutron stars. These are not particles. So what's the deal here? Well, how are we going to make progress? Okay, so we're going to consider what I call a black hole collider, which is instead we're going to imagine we can take these compact objects and we can scatter them. We can actually throw them at each other. They will interact. They will leave again in some sort of hyperbolic-like orbit. And the idea is that we're going to use these tools from scattering amplitudes and from the realm of particle physics to solve this scattering problem for black holes, and then we'll try to import the knowledge to this binary and spiral problem, which we actually care about for experiments. Okay, so that's the basic idea of this black hole collider. So let's define actually the particular problem that we want to solve. So the problem is, okay, so this is what we see at, okay, this is what we see in our detector. So this is actually the first detection of gravitational wave. This is just the raw data from LIGO, which you can see it's very noisy. Okay, so there's some amount of filtering that goes on, but actually the way that one goes from this to this, which are these beautiful detections where we have some prediction and we actually see this famous waveform, this gravitational waveform, is by having a theoretical prediction of what the signal should look like. And then essentially people take, so there's this process called match filtering, which is you take an inner product of the filter data with your prediction, divided by the sensitivity of the detector, and then you try to kind of minimize that distance. And that's actually how the detections are made. So it's not only for estimating the parameters of the binary, but even for the detection, it's very important to have these theoretical predictions. Okay? So it's fundamental to know what the signal will look like. Otherwise, we won't be able to find it inside of this very complicated signal. Okay, and to do this, we need to solve the two-body problem in GR. Okay, so we need to solve this problem of inspiraling black holes. And this is very hard. So the Einstein equations are famously complicated. There are a very large set of like nonlinear partial differential equations. Even the problem of whether they're kind of well posed and solvable is a hard problem, which actually was solved about half a century ago by Yvonne Choquet-Bruat, which just passed away last week, actually. She was a close friend of IHES. But there's been some recent breakthroughs in trying to solve these equations directly. So okay, it's some complicated equations, but let's just put them on a computer, right? That's what many people think. Okay, and indeed, in principle, numerical GR solves this problem. Just put in a computer, and there was a breakthrough about 20 years ago by Pretorius and friends, where they actually finally were able to do this. It was actually very hard, but they were able to simulate an actual black hole merger using numerical relativity. And since then, there's been incredible progress. But this is very expensive. So we need the, say, for instance, if you want to simulate something like 400 gravitational wave cycles, which is what you would need, say, for something like a black hole neutron star merger. This took, for instance, okay, so this is some paper from a few years ago, 8 months and a few million CPU hours. And we need actually hundreds of thousands of these predictions. So this is what these waveform templates look like. So this is just the parameter space, which are the two masses of the components of the binary. And each dot here in this plot is actually a theoretical prediction. So we need to populate these banks of templates and have all of these predictions to actually make a detection and to understand the systems that we are observing. Okay, and it's clearly impractical to perform all of those calculations on a computer. And even worse, there's many regimes of parameter space where the numerical methods break down. So whenever you have a large hierarchy, so for instance, if you have extreme mass ratios or if you have very large eccentricities, you might expect, and indeed you find that the numerical GR struggles. So for instance, even people can do now like mass ratios up to 10 or something like that. And also, if you want to now study other things, like, okay, we want to parameterize deviations from GR, then you would have to start all over, okay? Because then you have to kind of figure out how to solve some new set of equations, which will be even more nonlinear, et cetera, et cetera. Okay, so instead we will focus on analytical predictions, and these analytical methods will allow kind of generating these waveform templates at any point in parameter space, or at most points in parameter space, in a kind of a fast and efficient way, and also understand the effects in the signal of these different aspects of GR and its deviation. So for instance, you might ask, how does the spin of the binary precisely affect the signal without having to run a simulation every time? At which order should I expect some deviation from like spin very early on in the in-spiral phase? How do tidal effects enter this signal? Many other things you can ask, which is hard to disentangle from the numerics, but these analytical methods allow you to do this. and also to parameterize deviations from GR in some simple way. Okay, so this is what the events look like. So there's this kind of 3 phases of the compact binary merger. There's the so-called in-spiral phase, where the objects are still far away from each other. Then there's the merger, which is extremely nonlinear, where they merge into a single object, typically a black hole. And then there's the ring down, when this object relaxes down to kind of its ground state. And we're going to focus on this part here. So this is where we can use perturbative methods to solve the problem. And both numerical GR and black hole perturbation theory are kind of very successful at predicting this very late and very short piece of the signal. It's very short, but it's where most of the signal comes from. So it's important to have both a prediction from this longer but kind of weaker part of the signal, and for this shorter and stronger part of the signal. And the way that people find these waveforms, the way that we make predictions today, maybe not in the future. So we take different inputs, different calculations. So we take this, say, a 2-body Hamiltonian computed from GR. We'll explain how we do this. We'll take, say, the fluxes or radiation reaction forces for the binary. And then by combining these with insights with the test body limit, where we can do things nonlinearly in Newton's constant, and with numerical GR, people construct these waveform models that predict the whole signal. Okay, so there's a model that takes different kind of precise first principle calculations and combine it into something which agrees in all of the limits with the right thing, but it's some sort of phenomenological model. But these are very successful. This is how we actually make predictions nowadays for experiments. And perhaps the most famous of these models is the so-called effective one-body model, which was invented by Alessandra Bonanno and Thibaut Damour, my colleague, about 20 years ago. Okay, so the goal will be from this perturbative phase to say something about these sort of objects. And for these binary systems, we are in a regime where perturbation theory works because there's a small parameter, which is either kind of Rs over R. So the Rs is the typical kind of the characteristic length of the interaction, of the gravitational interaction. So it's the Schwarzschild radius, which has to do with the mass of the object. And then R is the separation between the objects. So as long as they are well separated, there's a small parameter, which is Rs over R. And then by the virial theorem, actually, we find that the velocity scales in the same way. So there's kind of V squared over C squared, or GM over R, scale both in the same way, and they're very small in this in-spiral phase. So this is the perturbative parameter, so that they're separated and they move slowly. Okay. And this is the realm of the so-called post-Newtonian theory, which has a very long history. So we are interested in small corrections to, say, the Newton's potential, which go like powers of V over C or GM over R. And for instance, so this is just Newton. The first correction is called the first post-Newtonian correction, which is actually computed by Einstein, Infeld, and Hoffman about a century ago. Okay, and then there's also the fluxes. So the fluxes, they don't have a Newtonian piece because in Newtonian gravity there are no gravitational waves. But for instance, this is just the famous Einstein quadrupole formula. But this is just the leading order approximation to an expansion again in small velocities and separations and large separations. Okay, so because these are kind of dissipative effects, they count like half orders in this post-Newtonian expansion, because they go like a single powers of V over C. Okay, so there's a long history in these calculations of in this post-Newtonian theory, where people have kind of slowly but surely been computing all of these corrections. Okay, so the 0 PN correction is Newton, which goes back about 400 years. Then 1 PN was in the late 30s by Einstein, Infeld, Hoffman. Then, okay, essentially every 40 years with some acceleration in the last few years, there's been progress in computing all of these things, especially again by my colleague Thibaut Damour and collaborators for the last 3 pieces. And the state of the art is this 5 PN potential, which is known up to a couple of coefficients. Okay, so we don't have the full information about this fifth Newtonian order. And just so that you have a rough estimate, what we expect that LIGO will be sensitive to is this 5 PN, maybe up to 6 PN order depending on the object that we're looking at. Okay, so this is about the sensitivity that we want to know for current experiments. Okay, so let's see. So just to see the first tests from LIGO here. So this is some measure of like the possible deviation. Okay, I won't explain in detail what this parameter is, but just think of this as kind of the bound on the probable deviation from the expected prediction from GR. Okay, so these first points here were just the prediction from the Hulse-Taylor pulsar, which was kind of the first indirect detection of gravitational waves. And there, basically, we were only sensitive to the quadruple formula. So this is just the quadruple formula and nothing else. And then we couldn't put any bound on the rest of the expansion. Okay, and this is the bound just from the first detection of gravitational waves. Okay, so even the first detection of gravitational waves already put a much more stringent bounds on kind of the possible deviations from the prediction from GR. Okay, so this is so the new experiments are very exciting because we're really probing gravity at a place where we didn't before. Yes.
You have posed an equation in V and G, but is there really when in experiments is there like a scale between them, or I mean, is it relevant to do they have the same order of magnitude? Or?
These two, yes, because it's a bound system. So very late in the inspiral, when they come very close, they both become large. But at the early inspirals, okay, for moderate eccentricity, so if you have very large eccentricities, they're slightly different, but roughly of the same order of magnitude. Yeah.
What is 0.5 on the previous slide?
This?
Oh, no, there, no.
Yeah.
Back one slide. There. What is 0.5 here?
So 0.5, here I'm just writing corrections to the potential. So for the potential, actually at the low orders, they're all like integer PN corrections. At some order, there's also kind of conservative radiation reaction, which can enter at odd orders, which I didn't write here, but these are just the ordinary kind of conservative corrections to the potential, yeah, which are always integers.
So how would the 0.5 correction look like there? Or for example, something like V times G or something?
There is no 0.5 for the potential.
Yeah. How would it look like?
V over C. It would look like a It would look like a V over C. So in the flux, yeah, it's like the flux. Yeah. It would. So these are powers of V squared. So it would look like a power of V instead of V squared. Yeah. Okay. More questions? Okay. So again, the goal is to start from this, which is the Einstein's equation, and compute these corrections. So for instance, yeah, this is Newton plus dot dot dot. Then there's like the fluxes plus dot dot dot. And all of these are predicted by GR. So in principle, we just need to solve these equations. But we're going to take a detour, right? So we are going to look at the scattering problem and see that actually there's certain separation of scales which will allow us to solve it. Okay, so here I'm just going to set up what the relevant scales are and what is the basic idea. Then I'll tell you what we've done, and then I'll explain some of the methods that we used. Okay, so the relevant separation of scales is that if you have some quantum system, you should have like the Compton wavelength being much smaller than the Schwarzschild radius to have like a well-defined classical limit. And then I told you that the separation needs to be much larger than RS. Okay, so the separation is like the momentum transfer in some scattering event. The Compton wavelength is like the mass, right? So here there's two hierarchies. So this Q over M tells you kind of quantum versus classical, and this being much smaller is just computing not quantum corrections, but just kind of computing the classical nonlinearities, right? But Q is a conjugate to R. So this is exactly GM over R. Okay, so these are the classical corrections which are small. So that means that when we compute these gravitational amplitudes for this black hole scattering, then there will be something that look like loops, but they have classical corrections hidden inside them, which are these nonlinearities. Okay, and the other relevant separation of scales that we use is that we also are looking at objects with the characteristic distance that the things are moving is much larger than the size of the object, which in particular can be larger than the Schwarzschild radius, say for a neutron star. And that means that we can replace this compact object, say a black hole, by a point particle with some given mass and spin. And in fact, because we like the tools from quantum field theory, we'll go even further and say that this particle is created by some quantum field. Okay? And we'll take the classical limit later. Okay? But we'll be able to use some tools from quantum field theory. So this might seem like an overcomplication at this stage, but it will become useful. Okay? And then we can systematically add any effects that we want. So we can add spin by making this guy. Okay, so here I wrote a scalar field. So this is for a spinless particle, but we can make it like a spinning field. We can add tidal effects, which would be nonlinear couplings to GR. We can add modifications of GR, just adding the usual kind of EFT corrections to GR. So here we have full control, and we can write any theory that we want. So I'm just going to tell you 3 things that we've done using these ideas, and then I'll explain kind of how we did it and what is the tool set that we've imported from particle physics and from colliders. Okay, so the first one is these new corrections to Newton's potential. Okay, I already told you about this post-Newtonian expansion, which is relevant for this bound problem. But there's an alternative expansion where we are slicing the same space in a slightly different way, which is called the post-Minkowskian expansion. And this is relevant for an unbound system. So when you have a scattering process, you can have these objects being relativistic. So in principle, you don't need to expand in small velocities. The virial theorem doesn't hold for hyperbolic orbits. So here you can have arbitrary velocity, and you can try to compute things order by order in Gm over R, so order by order in G Newton, but to all orders in velocity. Okay? And for instance, the first term is called the first post-Minkowskian. There is no zero post-Minkowskian because this already includes the Newtonian piece. Then there's 2 p.m., there's 3 p.m., and this kind of naturally fits with this scattering problem, this black hole collider that we like to think about. Okay, so using tools that I will tell you about later from scattering amplitudes, we've pushed the state of the art in these computations, and we've actually computed, so the community has computed both the 3 p.m., so the G cubed, so this is equivalent to a kind of next to leading order calculation, so something like a 2-loop calculation in terms of difficulty in classical GR. So this was done in 2019, and shortly after we computed even the G to the 4th, which is the kind of the 3 loops. And recently there's been a lot of progress at 5 p.m., which is the 4-loop potential and also other pieces that I won't have time to talk about. Also, but we don't know like all the pieces of this. Okay, so we don't have a complete prediction at 5 p.m. We just have some pieces of it, but there's been tremendous progress and very exciting things happening there. Okay, so and all of this has come, so these 3 orders have come using ideas from particle physics. Okay, so kind of the classical GR people were sort of stuck here, and then we've been able to push this state of the art pretty significantly. Okay, so what do these corrections look like? So this is just to show you that there's some real meat in these calculations. Okay, so the potential has an expansion in terms of these coefficients. The 4th coefficient, which is the G to the 4th, it's some function of the lower coefficients times these 3 objects here that I call M, which have something to do with the scattering amplitude. I won't go into detail. And these things look like such. So these R functions. They're just rational functions of gamma, which is the Lorentz factor, the relative Lorentz factor of the particle, so 1 over the square root of 1 minus the velocity squared. And then there's things like polylogarithms, there's elliptic integrals, so there's kind of very rich structure here, even though this is just classical GR. So for a long time, people thought that all of these special functions were something special about quantum field theory, but indeed they're just something special about field theory. And even in classical GR, we find a lot of this. Okay, so this contains all of the G4 corrections to Newton. So you can expand this in velocity to your heart's content, and you to any order in velocity, and you will find these answers that people have computed. So for instance, you can compare this to the 4th post-Newtonian order, which looks something like this. So this is just the 4th order. So this is the 4th order in velocity. Okay, so this is just a rational function, doesn't have these complicated functions, but you see that there's a lot of complexity here, which is resummed nicely into these neat functions of velocity. Even though I didn't show you these guys, but they're not very complicated, these R's. Okay, and I remind you that what we need is, even if you just care about LIGO and not about the future, will lead at least to push the state of the art to the 6 post-Newtonian order, and we are not there yet. Okay, so are these things actually useful? Okay, we've been able to do these state-of-the-art calculations. Are they useful? So actually our friends who construct these waveform models that are used in experiments are excited about these results, and they've all incorporated them into their models. So here's kind of a couple plots for a paper by Sandro Bonanno's group, and also a paper by Damore and a collaborator, where there's comparisons between, say, some resummed Hamiltonian, that is kind of one of the ingredients in this model, with the different perturbative data. So each one of these curves corresponds to kind of higher and higher orders in this post-Minkowskian expansion, with the best one being this solid line here. And this black line is the prediction for numerical GR. So this is the binding energy of the system as a function of kind of how many gravitational wave cycles before merger we are. And you see that actually the deviation is pretty good up until like 3 or 4 orbits before merger, where the error kind of shoots up above kind of 10%. Okay, but this is just one observable. So even if you compare for actually scattering problems, which people use kind of to tune the models. So this is in this paper by Thibault and friends. They compare the actual kind of resummed scattering angle, given this data from perturbation theory, using the model that goes into the waveforms with the prediction from numerical GR. So these data points here with arrow bars are the predictions from numerical GR, and the blue line on top is kind of the resume, like the model which uses the state-of-the-art data from these 4 post-Newtonian calculations, due to the 4 calculations. And you see that it's much better than the previous orders, which especially for kind of small values of angular momentum, they go way off. Okay, so people now are working into actually incorporating these predictions in the waveforms that go into these templates. And there's even collaboration with people from our community from scattering amplitudes. Okay, what about new physics, other things? Okay, what are we excited about in gravitational wave physics? Kind of black holes, testing GR, all of these things, right? So for instance, a place that people have kind of or an area that people have devoted a lot of attention in the last few years is a so-called study of tidal properties of love numbers of compact objects. So what is a love number? So say we have a black hole or some compact object, and then we ask, okay, if we put this object in an external field, so this is some like kind of a gravitational field, what is the induced quadrupole moment of this field that encodes the tidal properties? So it's kind of the gravitational polarizability of this object. Okay, so this is captured by some set of coefficients for each multiple moment. And then having analytic control over these waveforms allows us to understand how they appear in this waveform. Okay, so even in this post-Minkowskian expansion, this was understood also in the post-Newtonian setting, but in the so we know that the leading coefficient enters at 5 pn. So for instance, if you want to taste, so this is for black holes, neutron stars, for any object, because this is some coefficient in this effective theory of the point particle that I mentioned. Okay, so for instance, if you want to test the tidal properties of neutron stars to try to learn something about its equation of state, you know that you will need to go to this order and have a very good prediction of what you expect there. Okay. Also, interestingly, these ones, the leading tides, which are kind of the response to a static field, they're 0 for black holes in 4-dimensional gravity. So this is very interesting, and also it tells you that it's a good place to test general relativity, because we can try to put bounds on these coefficients, and there's even a few papers, recent papers, I won't have time to show the plots, that put the first bounds on some of these tidal coefficients from actual data. Okay, so this is an excellent window in this new physics, and we can actually also use scattering amplitudes to compute these things, especially for black holes. So instead of doing this linear response calculation, which is subtle because it's a coordinate-dependent calculation, there's been a lot of confusion over the years with this. There's other methods. For instance, you can compare a calculation in this kind of black hole setting, so scattering gravitational waves from a black hole, or for your favorite model of a neutron star, with a prediction for the same kind of Compton-like scattering in the effective field theory, where you replace the black hole by a point particle. Now, this has some undetermined parameters, which are these tidal coefficients that you can fix by comparing this. Actually, some people here have done pioneering work in this direction. So, for instance, Fabian, I couldn't find his picture, but he's also had a few papers on the same topic. And we can also understand how kind of extensions of GR, kind of EFT corrections to GR would modify the potential. So, for instance, if you take the leading one in 4 dimensions, which is the arc to the cubed interaction of 3 gravitons, so this is some kind of exotic gravity interaction, which should be very suppressed by some high energy scale, but we can also compute precisely what is the correction to the potential, for instance. Okay, so this tool set is kind of very versatile, and it lets us do many things. And okay, you can also choose your favorite theory and repeat this calculation, and there's been a lot of progress in that direction. And then finally, we can also compute not only potentials, but radiative quantities. And this uses some very nice formalism, which was set up by David Kosawer from here, and also there's been important work by Carlo along these directions. So also using scattering amplitudes, we can compute, say, the radiative momentum, energy and momentum from the scattering event. And the idea is that, what is that? We just need to compute the cross-section for emission of gravitational waves, and then weight it by the energy, and then do the integral or the final phase space. And this is some sort of like cut, some sort of like cross-section like object, very similar to things that people compute in colliders, where you sum over all states and all final states with a specified initial state. Okay, and this again, it's some fixed order in G. So people have computed, okay, in post-Newtonian, people have been computing slowly over the years, but now there's been a lot of progress at order G cubed, G to the 4th, G squared, which I won't summarize. But and there's also surprising relations with the bound problem. So, for instance, the leading order energy emitted in the scattering process, there's some nice formula which tells you that if you analytically continue it to negative energies and average over the sign of the angular momentum, then you actually get the right answer for the inspiral problem. Okay, so you can even access directly observables for the bound system, which we care about for experiments, from these calculations of scattering. And if you don't want to go through this, you can also extract the fluxes. Given the total energy, you can kind of infer the flux of energy and angular momentum, and then use those to compute your orbits in the bound case. Okay, so this is a kind of a quick summary, kind of flashing 3 things that we've been able to do with this. In fact, all of these things are already a couple years old. There's been a lot of exciting progress. I'll have a slide at the end where I list a lot of the recent progress. But it's just to give you a flavor of what we can do using these tools and this program. Okay, so what are the tools? So now I'm going to tell you a little bit of how we do this technically. And the strategy is to use ideas from scattering amplitudes, effective field theory, the so-called double copy construction, and unitarity. Okay, so in principle, the textbooks tell us how to compute these scattering amplitudes, right? We just say, okay, just draw all possible diagrams, right? And then compute in perturbation theory to the order that you want by summing the contribution from each possible Feynman diagram. Okay, each diagram is a function of momenta, polarizations, etc. And all of these particles here generically are virtual. They don't satisfy Einstein's equation. But if you've ever done any computation beyond the 3 level, you know this gets out of hand pretty quickly, especially in gravity, which is very nonlinear, right? But from these gravitational amplitudes, we can easily extract these various quantities that we're interested in. For instance, if you just look at this leading order diagram for graviton exchange between 2 massive particles with mass m1 and m2, then you find that the answer is this, where again this gamma is the Lorentz factor, the relative Lorentz factor, and this q is the momentum transfer. So it's q squared is a momentum transfer squared between the 2 particles. And then if we just compute the 3D Fourier transform of this, then we find indeed the Newton's potential and the velocity corrections at the order g. Okay, so it's a very simple calculation where 1 Feynman diagram gives you the whole 1 pm potential. Okay. From the point of view of classical physics, what we are doing is we are solving Einstein's equation perturbatively, and we're just solving for the field on this particle, and we're evaluating in the other particle. Okay. But then if you go to high orders, it becomes much more complicated, right? So first of all, inside of these loops, there will be classical and also quantum corrections. So it's useful to expand in the classical limit to focus on on the part that we care about. And remember, I told you that the classical limit is saying that Q over M is small, so that you can expand in the large masses of these objects. Okay, and but this gets very complicated. And oops, I think this slide. Okay, I don't know what happened. There was some issues with the PDF that we thought we fixed, but okay. So even the rest is missing. I will just try to explain with this picture. So more generally, what we do is we say that whatever these local interactions are, we can replace them by a potential, right? And then by computing amplitudes with this potential, which is kind of an ansatz with 3 coefficients, and it also includes loops. So for instance, this diagram here involves 2 insertions of the Newtonian potential. So there's part of this which we already know if we computed the order G answer. So we need to subtract from this the kind of 2 insertions of the leading order potential, but then the high order diagrams will encode the new contributions. Okay, so this was explained here in pictures, but something happened. And okay, also this was explained by kind of Ira Rostin, Cliff Chung, and Michael Solon. So all the references are gone. Okay, but anyway, so the idea is that from these computations of amplitudes, we can match to some EFT where we just have particles interacting through a potential. So we integrate out the gravitons to construct this potential. This is allowed because these gravitons are very off-shell. So that's typically when we talk about potentials, we are not talking about on-shell gravitons that are escaping to infinity, that are actual radiation. So this is a well-defined process. So once we have this potential, we can just use it for the in-spiral problem. Okay? We computed it using this black hole collider, this black hole scattering process, but then we can actually use it to make predictions for the bound system because the potential is the same for both. Okay? So then the goal is to compute this gravitational scattering amplitude from which we can, say, extract the potential. So how do we do this? So one trick that we use very efficiently is to relate amplitudes in general relativity, so amplitudes that involve gravitons, to amplitudes in gauge theory that involve gluons. So these are in principle very different, right? So okay, so we know that the understanding of the kind of strong and weak forces has to do with non-abelian Yang-Mills theory, so kind of non-abelian gauge theories, which look like this. So you have some field strength for some like color field, and then this has some like nonlinear pieces. So there's kind of 2 types of interactions between gluons or W's. There's like 3-point and 4-point interactions, and these encode basically everything we know about these forces in particle physics. But gravity is more complicated because it's much more nonlinear. So if you just expand perturbatively the gravitational action, you will find that there's vertices in your Feynman diagram, so Feynman rules with any number of graviton interactions. Okay, so this is very complicated. But there's some like magical relationships between amplitudes in gravity and gauge theory. So for instance, if you take the 3-point amplitude for gravitons, then you realize that it's literally just the square of the 3-point amplitude for gluons. So the probability amplitude for scattering like 2 gluons into another one is simply related to the one for gravitons. And similarly, if, for instance, for the 4 graviton scattering, then you find that the squaring relation is something like this. You just need to multiply it by the center of mass energy squared. And there's a systematic understanding of all of these relationships to higher orders. Okay, so this is just 2 kind of hints of a very general story, which goes by the name of the double copy, that lets us compute these amplitudes in a very simple way. So these are all like 3-level amplitudes, so kind of leading order imperturbation theory. And there's also similar kind of intuitions and precise relationships for classical solutions. So if you take like kind of the field of a point charge in a particular gauge, you can relate it to kind of black hole metric also in some particular gauge, as was shown by these guys here. Okay, so there's all of these relationships between gravity and gauge theory that we are able to exploit when we do these calculations. Okay, so but we still need to compute these nonlinear things. And I told you that these diagrams, all the particles don't satisfy Einstein's equation, so they're not actually real particles. So how do we use these simple building blocks? Okay, so first of all, there's simplicity in the actual amplitudes compared to the diagram. So these are very typical slide that you might have seen in another talk about scattering amplitude. So if you look at the 5 gluon amplitude. If you just use Feynman diagrams, there's about 15 diagrams that look like this, with these off-shell particles. And then if you just print this in your computer, it's kind of 24 pages of things like this, which are like products of momentum polarizations for the 5 gravitons. Okay, so this is what one of the terms here looks like, for instance. Okay, and it only gets worse in gravity. So actually, you can count that if you go to like around like 25 gluon scattering, if you count how many terms there would be, it's already like more than atoms in our brain. So so it literally doesn't fit in your head. Okay, but amplitudes are simple. So if we actually plug in their polarizations and we sum all of these things, then we find that, for instance, this 5 gluon amplitude, it collapses for these particular choices of the helicities into this very simple formula, from which then it's very easy to guess what the amplitude for any number of gluons looks like. Okay, so indeed, for any number of gluons, you just need to add more factors like this in the denominator, and the pattern is clear. Okay? And we can actually show that this is correct. Okay, so these amplitudes are simple, so let's try to use them as building blocks. So these are kind of leading order imperturbation theory amplitudes. And the trick is this so-called unitarity method, where we use, okay, unitarity is basically the idea that probabilities add up to 1, so that we can insert complete set of states. And okay, we know there's things like the optical theorem that tells us that the imaginary part of amplitudes can be broken down into kind of simpler amplitudes. We can actually choose some particular process, and if we put a bunch of the legs of some diagrams on shell, so if we require that they satisfy Einstein's equation, this process will factorize into smaller processes. Okay, and so the amplitudes on particular places in momentum space, they need to separate into products of smaller amplitudes, and this was kind of developed systematically also by David, who's from here many years ago, and collaborators. So we can break down this complicated process into smaller physical building blocks, and this is how people do computations for actual like QCD processes for colliders nowadays. One of the ways. Okay, so we can kind of reuse, reduce, and recycle our knowledge from previous orders to compute things at high orders. And this is much more efficient than Feynman diagrams. For instance, this G-cubed calculation, this first state-of-the-art calculation that was done using these methods from scattering amplitudes, instead of having to add a gazillion Feynman diagrams, which are very complicated, you just need to compute these 3 kind of, so these blobs are amplitudes, so these are just some products of amplitudes where we sum over kind of the polarizations of the intermediate state. So these kind of 3 simple pictures, which are built out of 4 graviton amplitudes, or 2 scalar 2 graviton amplitudes. The most complicated is 2 scalar 3 graviton amplitudes. These simple pictures contain all of the information that you need to compute the amplitude to the order that we need. Okay, so in summary, what we do is we compute these scattering amplitudes in gauge theory using unitarity. Then these blobs, they satisfy the squaring relation, so we can get the ones in gravity for free. And then we can extract, say, the potential or other observables by comparing to IPhT or directly computing them, like in these formulas by David and friends that I showed you. Okay, so, and as I summarize, using this strategy, some of the things that we've done is computing new corrections to Newton's potential. We've characterized kind of the effects of tides and new physics on observables and computed them. And we also computed things like radiative fluxes for gravitational wave scattering and also for bound systems. Okay. Actually, I have left many things out. There's been, especially in the last year and a half, there's been tremendous progress. So for instance, there's been recent progress on the next to leading order waveforms for scattering that many people here, like Stefano, have made important contributions to. And this is kind of first progress since the 1970s. So the leading prediction was done by Kovacs and Thorne in, I think, 74. So we had to wait 50 years to have the kind of next order. And I think we have ripe tools to actually push this. There's been also recent progress on the potential at this order. So this is kind of almost as hard as a for-loop computation in kind of gravitational perturbation theory. Okay, there's been a lot of progress for spinning binaries. For instance, Fabian has worked a lot on this. For an extreme mass ratio binary, so this is an important problem because this is what we're going to see on space-based detectors, and this is kind of a very nonlinear regime where kind of perturbation, the usual perturbation theory breaks down, but there's ideas of how to kind of merge different approaches. There's ideas about running of these tidal effects, which actually there's some renormalization group. There's thing called tails and memories that tell you about kind of non-local effects in time in the waveform. So there's a kind of very rich story that's developing, and that to each one of these points, we've been able to kind of contribute something using these ideas from particle physics and scattering amplitudes. And actually, many people here at IPHT are making fundamental contributions to this area and pushing the state of the art in many directions. So I think you guys are lucky that have really great people around. And okay, so hopefully I convince you that these black hole colliders are useful to understand the dynamics of classical gravity. And I'd say that there is a long way to go and a lot of work to do, because we're going to have new experiments coming up. We're going to have space-based detectors like LISA that are already kind of scheduled to come up in about 10 years, maybe a bit later. Things like the Cosmic Explorer, like new ground-based detectors that will probe like kind of all of the events in the observable universe, more or less. And we need to keep pushing the state of the art and provide this kind of valuable theoretical data and predictions that will be important to achieve the scientific goals of all of these experiments and overall of this program of gravitational wave science. And I think along the way we'll discover also new structures like we've done in this world of scattering amplitudes. And I think this is only the beginning. So the gravitational wave science is in its infancy, and the future looks bright. And I think particle physics can and will be a part of it. And I think we're already making important contributions to this area. So I think I'll end there. Thank you very much.
Julio, for the great talk, and let me emphasize that Julio has not been corrupted or bribed in any way in order to speak so highly of IPHT. He did in his own free will. So let's floor is open for questions.
Thank you. You had an identity between the quantity for in-spiral case to the with the analytic continuation of the scattering one.
Yeah.
Is that valid to all orders? Where does that come from?
So it's not valid to all orders because of these non-local in time effects. So let me go back and find it. So it comes from the fact that this quantity here, this flux, the instantaneous flux, actually is the same for any orbit until these non-local in time effects come in. For instance, for electromagnetism, there are no such effects, and this formula would be precisely exact. And the idea is that this instantaneous flux is the same for any orbit, and then the orbital elements, so things like the distance of closest approach or the periastron distance for like a bound and a scattering problem, they satisfy certain analytic continuation. So you have some integral of these local quantities that gives you this, and then basically by analytic continuing the endpoints of this integral, then you can find these relationships. Unfortunately, in gravity, they break because of these tails, which are these non-local in time effects. But for instance, recently, okay, so maybe I'll advertise. So some of these tails, so there's conservative tails and dissipative tails. But for instance, recently we found also some relationships between kind of, so the dissipative states have to do with the fact that these tidal coefficients run, or that the multiple moments of the binary, they undergo some renormalization group. And then we found, again, some relationship with scattering. So we can compute kind of these certain coefficients of logarithms, which are precisely the things that break these formulas, which have to do with some anomalous dimension by relating it to a scattering phase shift. So this is also a formula that has kind of the same spirit, that you can go from scattering to something which is universal or something that is valid for bound. So I have hope that we'll be able to kind of, at least to a few high orders, we'll be able to kind of really relate these observables between scattering and bound. Otherwise, we just have to go back to these instantaneous quantities. So we will always have to go through things like the fluxes, yeah, like this, and then compute for the new orbits. Yeah.
Thanks for the very nice talk. I have a question about using the cutting rules or the unitarity method to compute the amplitude. So when you do it, you only get the imaginary part and you're missing the information about a asymptotic region.
Yeah, so we actually don't use the optical theorem per se. So what we use is the so-called generalized unitarity. Okay, so this optical theorem was just for inspiration. That if you take the amplitude written as an integral, so as a loop integral over some loop momentum space, then it's an integral of some rational function. And then that rational function is the thing that satisfies this property. So if I take that rational function and I kind of compute the residue on the location where some particles go on shell, and I sum those residues for all possible diagrams, they will reorganize themselves into this expression. So it's not that we are computing the imaginary part of the integrated amplitude, we are computing the integrand that then when you integrate it will give you the full amplitude. And we just use kind of the residues at different locations in momentum space to infer its totality. Yeah.
But what you get is the imaginary part of the integrand.
No, we get the integrand is a real rational function. So we get the full integrand.
Julio will be around also in the afternoon and is going to stay in the visitor office close to the secretaries, so feel free to bother him later. Thanks again everyone for coming, and let me just conclude by thanking again the speaker, thanking you, and thanking also our technical team who did a great job in helping us with the setup, of course. So see you next time.